Okay, so we're going to talk about inventory analysis in this video and link that to decision analysis. So we're going to start with this example where we have a machine repair person problem. It's called the newsboy methodology that we're going to illustrate in this example. And here what we have is we have a machine tooling company that the manager has to decide on how many repair persons to hire to service the equipment. So the machine works, the plant operates during the day, and during the night time repair persons work on the machines that have failed during the day. Each repair person can repair one machine during the shift. So if for a given day there are more machine failures than there are repair persons, the additional machines must be repaired during the night shift by an outside contractor at a cost of $150 per machine, while the permanent hires, the company that can hire repair persons, that can cost only $50 per day. So the number of machine, so you can see here, if we have machines don't fail and they have repair persons, we paying them and doing nothing. And if we have machines that fail but we don't have repair persons, we're going to have to pay much more by hiring outside contractors. So we're going to balance these two costs. So the source of randomness here, which we don't control, is how many machines fail every day. From previous experience, we noticed that machine fails according to this probability distribution. Remember, anytime we have a source of randomness, we model that as a probability distribution. In this case, it's a discrete distribution. And so past experience shows 20% of the time we had 0 failures, 30% 1 machine failure, 30% of the time 2 machine failures, 10% of the time 3 machine failures, and 10% of the time 4 machine failures. And so that gives us the probabilities that add up to 1. So the objective is to determine how many permanent hires should we have, repair person hires, to minimize the average repair cost per day. So demand is uncertain, and so we have to model that. So we model that as a probability distribution, and this is the graph of the probability distribution for the demand. And if we find its expected value, we use D for demand. The expected value is 1.6, which is probabilities times the corresponding values, add them up. We also can graph the cumulative distribution, call it F, capital F of D, for the cumulative distribution, or probability of D less or equal to D. And this is the graph. 0 failures happen 20% of the time, 0 or 1 50%, 0, 1 or 2 80%, 3 or below 90%. Of course 4 would be, or below, would be at 100%. Second thing is we notice that we have a fixed understocking cost per unit and overstocking cost per unit. The unit understocking penalty is $100, which is the $150 we pay for the outside contractor minus the $50 if we had a permanent hire. And the overstocking penalty is $50, which is if we have more people hired than machine failures, it's going to be $50 for each one of those. Now the objective is we want to select a stocking level, call it Q star, that minimizes the expected value of the total penalty cost. Let's call it PE, penalty cost of Q, where Q is our decision variable on how many repair persons to hire permanently. And the minimum expected penalty cost is going to be expected value of PCQ star. So we use the following notation, just to recap. D is the discrete random variable, small d is values, f of d is the probability distribution of d, capital F of d is the cumulative distribution, q is the decision variable on how many units to stock or how many permanent hires to have, q star is the optimal value, cu is the cost of understocking, in this case it's $100, co is the cost of overstocking, which is $50, penalty cost if q units are stocked and d units are demanded, so we hire q but d fails, and that's the expected value of that, right? So the solution methodology, first we look at the penalty cost function. It has two forms, one when we have excess demand, one when we have excess supply. So in the case more machine failure than I have permanent hires, for each additional extra machine is going to cost me, that's an understocking cost. So if I have 2 times 100 would be $200 and so on. If I have excess supply, I hire more people than machine failures, then I have to pay them $50 each for those excess. So that would be a penalty for not hiring exactly the same number of permanent hires as there are machine failures every day. Right? So under the assumption of probabilistic demand, we seek to minimize the expected value of the penalty cost. So now we find the expected value, so it's going to be PCQF or QD times F of D. So what's the cost times the probability of having that cost? And so as long as D is less than Q, I want to have overstocking, so I'm here. So D is less than Q, so D goes from 0 up to Q, and I have Q minus D, excess supply times the overstocking times the probability of that. This mu should be 1, so D equal Q plus 1 to infinity. We can give it different values to deal with the continuous case, which we're not dealing with here. So in this case, I have the excess demand, and that's going to be D minus Q, my extra demand. And there's understocking cost times the probability of having D units of demanded. And so I add all of these together and do some tedious manipulations. I'll end up with this relationship, which basically I compute cost of understocking divided by cost of understocking plus cost of overstocking, get a ratio, and that turns out to be greater than, and using the cumulative distribution, at Q star minus 1, but it's less than F at Q star. And so this allows me to find out the optimal Q star. Okay. And the way we do that is first we compute this value, which is in our case, was it understocking, is a 100 over 100 plus 50, so that's 100 over 150 or 2/3. And so if I take my distribution here, F of D and F capital D, so 2/3 is going to be above 0.5 less than 0.8, and that tells me I need to have, my optimal hire is to have 2 people hired. Okay, I can do it either with F of D or with F of, so graphically here you can see these are the calculations, we have it here, and so the 0.5 is here and the 0.8 is here and my 2/3 is here, so I go along this axis, that's the number there, go all the way here, go down, and that gives me my optimal hires, which matches this equation I have here. Okay? Now, so thus Q star equal to is my minimum expected additional cost. So that's the additional cost due to uncertainty. Okay? sorry, let's go back. The minimum expected additional cost. So this is the penalty cost. The minimum expected additional cost due to uncertainty is the minimum value of the expected penalty function. Uh, so if I hire 2, what's going to be the expected cost or the additional cost, because I either end up with overstocking or understocking? And so that's, I make Q star equal 2 and repeat those computations I had basically here. And for Q star equal to, that's easy to do. So that's, I have here, if I hire none, that's going to be, sorry, if I hire 2 but 0 machine failures, that's going to be the cost. 1 machine failure, that's going to be the extra cost. 2 machine failures is going to be 0. That's for 3 machine failures. So I have 1 going to be handled by an outside contractor. And if I have 4 machine failures, 2 of them will be handled by an external contractors, and that's at 10% of the time. So that gives me $65 per day. So now, if we had perfect information, a crystal ball, that is, we are able to hire exactly the same number of people as machine failures, we still have to spend $80 per day on machine failures, and we call that's the total cost if I had perfect information, because in average I would have 1.6 machine failures. Each one will cost me $50 permanent hire, and that would be $80. So if I add these two together, the cost of perfect information, total cost with perfect information, plus the cost of uncertainty, that's going to be my expected total cost without perfect information. Or I can do that by just doing the expected value. If I hired 2 people, but now I factor in the total cost. So if I have 0 machine failures, it's going to cost me, I have 2 people on hand, that's the cost. 2 machine failures, still going to be, I have 2 people on hand. 3 machine failures, I still have 2 people in hand. Sorry, this is for 2, yeah. If 3 machine failures happens 30% of the time, this is the cost of the 2 I have on hand plus the outside hire. And the same thing if I had 4 machine failures at 10% of the time, that's the 2 people I have on hand plus the 2 outside contractor cost. And so that gives me 145. And so now the expected value of perfect information is the expected value, the expected total cost without perfect information minus the expected total cost with perfect information. And that turns out to be the expected penalty cost. So the expected penalty cost is the expected value of perfect information. So the $65, that's the expected value of having perfect information. Okay. Now, so this seems to be same terminology we used in decision analysis, so but using regret criterion, expected regret instead of expected payoff, because we're talking about cost here. So can we set up the problem as a decision analysis problem? And the answer is yes. So here I have my states of nature. State of nature 0 breakdowns, S2 1 breakdown, 3 breakdowns, sorry, 0 breakdown, 1, 2, 3, and 4 breakdowns. These are my state of natures, and these are their probabilities. I have them here. And now my decisions can be 0 hire, 1 hire, 2 permanent hires, 3 permanent hires, or 4 permanent hires. And now let's look, how do we get the payoffs? So let's look at 0. If I have 0 permanent hires and 0 machine fails, that's going to be no cost. But if one machine fails, I need an outside contractor at 150. If two machine fails, I need two outside contractors for $300. If three machines fails, it would be three outside contractors at $450. And the same thing if I had four breakdown would be $600. So that's negative for cost. Let's do, if I had one machine, one permanent hire, if no machine breaks down, it's still gonna cost me $50. If one breaks down, it's gonna cost me 50. If two machine breaks down, it's gonna cost me 50 plus the 150, so that's negative 200. If three machines break down, it's gonna cost me the 50 plus two outside hires, so that's gonna be 350, and so on. So I got all my, of course, if I have four permanent hires, it's going to cost me $200 if I have zero machine breakdowns, or one or two or three or four. Now we're going to change this table into a regret table first, and we know that this would be my if there are zero machine breakdowns, the best decision I can do is to have zero hires, so that would be my zero regret. And I can get those regrets here by taking 0 minus negative 50 minus negative 100 minus negative 150, and so on. If I have one machine breakdown, the best decision is to have one machine hire, so that would be 0 regret here, and the regret here would be the difference, and so on. I can get all the regrets. So working this that way, I will get this would be my regret table. And now I have the probabilities here, so I take those probabilities of the states of nature, multiply them by the corresponding pay or regrets for zero permanent hires, gives me the expected regret of D1. Multiplying for this row, I get the expected regret for D2, and so on. So if I were to look at the minimum regret for all these 5 decisions, is going to be $65, and that's the exercise you are asked to complete. And you can see how this really fits well with the decision analysis model. Okay, thank you. Hope this was helpful.